Yeah, now we've learned about how we classify different reservoir fluids and how we differentiate them from each other. And now we're going to try to bring it all together and do a short exercise on this topic. But before we go there, we can start and become a little bit more familiar with at least some rule of thumbs for different reservoir fluids. So a very good place to start is just to look at some generic examples of different compositions and associated properties for different fluids. This is from the SB. Sorry about that. This is from the SB phase behavior monograph. This table, and you can find similar tables in other resources as well. Actually, the the one resource that we recommended you to read before the course in one of the first videos actually has a similar type of table. The first thing that we can take a look at is the compositions. Here, as we've learned about, we have two non-hydrocarbon components, CO2 and nitrogen, and then we have a range of hydrocarbon components right here. What we see is that for the black oil case, we have almost 56% C7 plus, and actually the trick when it comes to understanding at least compositions and its impact on reservoir fluid classification is actually to understand that what probably is one of the key parameters determining and differentiating one reservoir fluid from another, at least from a compositional perspective, is the C7 plus amount. So if we remember back to the slides, we said that okay, a black oil typically has a C7 plus content of that's higher than 25%. This is the case here, and when we go below 25%, as is the case for a volatile oil, we typically step that into the volatile oil range. On a rule of thumb basis, we like to say that maybe around 12.5 mole percent C7 plus. That's where we, at least on a rule of thumb basis, have the critical points. That's around there. Some places where we transition from a gas condensate into a no from a oil near critical oil to a near critical gas condensate. But that's on a general basis, and we see just by looking at this near critical oil example right here that actually that's in this case a bad type of rule of thumb, but it's at least close to that point. At least what we know is that if the C7 plus mole percentage is like 8%, I can almost guarantee that it's a gas condensate on a general basis. And as we go further down to something that's leaner, I guess the more lean a system is, the more to the left on this particular table we're going. The second thing to note about C7 plus is like, okay, it has an impact on how we classify a reservoir, but it also is it's a very good proxy of the components that translates into stock tank barrels at surface. Stock tank barrels meaning, okay, actually the volume in the reservoir or the components in the reservoir that remains and essentially makes up the liquid phase that translates into sellable stock tank oil, so what we make dollars from. That's why there's no coincidence why the dry gas doesn't have any of these components. Okay, that's not a coincidence. That's because there is essentially no components in the reservoir that at surface can actually form a liquid phase, because at surface conditions all of these guys right here, they remain in the gas phase. What we see for the wet gas reservoir is that we have components in that C5 to C7 range. Depending on how efficient your surface process is, components that are higher than C5 plus, C6 plus, or C7 plus is a good proxy of things that make up essentially stock tank oil. And that's why we have components of that in the wet gas. And the more you have of these components, typically the more, I guess, at least per reservoir volume, oil you'll sell at surface, and lower your GOR is, and the higher, and also the lower your formation volume factor is, which on a generic basis is good. The thing to notice here, there's a lot of different values on this axis as well. This is molecular weight of C7 plus. This generic trend is true in general, that for the leaner your system becomes, then the leaner, or the lower molecular weight of that C7 plus becomes. That's directly actually related to specific gravity, or which is directly again linked to liquid API. So there's a few things that we can sum up here in the end that's important to note, but these three guys right here is more or less linked. We discussed this KW right here, that's the Watson characterization factor, and based on these values we see that we have a value that's very close to 12, which on at least a generic basis can be categorized as something neptanic. Going over to the GORs and OGRs, which is just two ways of at least mathematically describing the same thing, we see also how that range for the different fluids. Where this trend is true in general, lower GORs is related to the more black oil. When we increase the solution GOR, we're getting to the volatile oil region. We're coming into something that's considered near critical. And then once we go substantially above that and we're into the gas phase, we can have a rich gas condensate reservoir, as for instance what we see right here. And when we go into the wet gas phase, our GORs is typically very high. And then it makes more sense to actually talk about CGRs, where the units that we use is or CGR or OGR, which is just two different names for the same thing, where we use the units of stock tank barrels per million. Good. The last thing, which is not necessarily very correlated, it can be a little bit arbitrary, is the specific gravity of the produced gas at surface. And as we see here, it actually is the lowest in this particular case. It increases a little bit before it starts to go down again. So it's hard to say something generic about gas-specific gravity. And we also see how saturation pressures are also changing for the different cases right here. So just to sum up, just a couple of key points. And yeah, I'm not going to brag about my writing skills, but I think they're serving a purpose here, I hope. One of the most important properties in terms of, at least from a compositional standpoint, to know and care about, at least from if we want to classify reservoir fluids, is C7 plus. And the amount of C7 plus, very important. We also know that that's what like C7 plus components, or components close to C7 plus and higher, is what actually translates into stock tank barrels. Stock tank barrels is again what translates into money, which is how we develop oil and gas resources. Again, probably the last thing to mention here that's also important is that the molecular weight of the C7 plus, which is important, is very much linked to and correlated to the specific gravity of C7 plus in some way or another. And this relationship can change from one basin to the next. Good. So now I've hopefully conveyed a couple of key concepts, but hopefully also confused you a little bit, because now the exercise is actually starting, and it's about this particular table. And the goals and objective of the exercise is to understand fundamentals of reservoir fluid classification. And the exercise is two different questions, very, very simple. The first one is you're producing from a gas reservoir in which the producing CGR/GOR changes with time. What type of gas reservoir is this? And then from the reservoir or the classification point of view, we have three different gas reservoirs. It can be the dry gas reservoir, it can be the wet gas reservoir, or it can be the gas condensate reservoir. So picking which of those that is the correct one, that's the first part of the exercise. The second part of the exercise is actually what is wrong with the table that we looked at the previous slide. And I made it a little bit simpler right here. So what's wrong with this particular table? That's the questions. Good. So I'll go back to exercise 1, and at this point, if you like to give yourself an honest attempt to answer these questions, you'll pause, you'll try to answer these things, and then you'll unpause, and I'll give you the answers. So hopefully you've paused now and answered these questions, and I can now give you the answers. The first thing that we know is that we have a gas reservoir, so we're producing from something that's at least gas in the reservoir initially, or it's classified as gas, as that limits us to 3 different alternatives, which makes it a little bit easier. And the other thing is that we know that the producing condensate gas ratio, or GOR, changes with time. And that leads to the follow-up question: what type of gas reservoir is this? So we know that the GOR of a dry gas reservoir, so if we start with the dry gas, we learned that the producing GOR for dry gas is always infinite. For wet gas, we learned that the producing GOR is always equal to 1 over the solution GOR, also sometimes called the vaporized oil ratio in places like Eclipse, Harmony, ResFrac, and other simulators probably too in the industry. So we know that these are constant. And for actually the producing GOR to change, the producing composition has to change. And for the producing composition have to change, we have to be able to, at some pressure at least, go into the two-phase region. And if we have a two-phase region and we have a gas reservoir, we have a gas condensate reservoir, which means that the correct answer to question 1 is that this is a gas condensate. The second question, the answer to the second question is what's wrong with this particular table. Many times when we do this, I get all kinds of different answers. The first thing is that something that confuses people is, in the wet gas case, we have more C1 than in the dry gas case, and like, is this the correct answer, or is this inconsistent? Well, but what did we just learn? What we just learned is that the trick, and what is the most important for reservoir fluid classification, is C7 plus mole percentage of the fluid. And that is what determines whether or not we have liquid on surface or not. We know for sure that these methane molecules, most of them will go into the gas phase at the surface. So that's really not relevant. So this is not a problem with this table. Okay, and there's all kinds of other suggestions that I get when we do this exercise, but it's not related to that. What we learned about when it comes to wet gas reservoirs is that wet gas reservoirs, it's outside, or it's actually there you have a reservoir temperature that's to the right of the Cree-Condon term. So just to make sure that we have repeated that, we have the Cree-Condon term here, and then the T reservoir is here. This means that if this is our initial reservoir pressure, and we deplete down to some bottomal or minimum pressure right here, we're producing with a surface process inside of the two-phase envelope, but at the reservoir temperature in the reservoir, we're always single phase. So we should not have a dew point. So wet gases does not have a dew point. Okay, and that's what's wrong. So this is most likely wrong, and if you found this is a table in the SB monograph, if you have that, on phase behavior and PVT by Whitson and Brule, and if you know this, you're already one up on the monograph. Congratulations.